Hello everyone, my name is Fabio Patrone and I'm going to present you our work whose title is Smart Gateway Diversity Strategies for KV Feeder Links in SDN-Satellite Networks. Nowadays, both industrial and research community are pushing satellite communication networks towards an integration with the terrestrial ones, especially within the 5G framework. Services, and in particular enhanced mobile broadband services, will benefit from this integration, especially thanks to the ubiquitous coverage and multicast capabilities of satellite communication networks. However, in order to fulfill the 5G key performance indicator and guarantee the user's quality of experience, satellite links has to offer higher data rate. One way to achieve this goal is to move towards higher frequency bands, such as QV or W band. However, additional technical challenges, and in particular additional attenuation factors such as the water absorption, take place in these frequency bands and has to be considered in designing proper countermeasures. The concept of smart gateway diversity has been defined to overcome this issue. The main idea consists in defining a terrestrial segment composed of more ground stations located far away from each other, at least 100 km, in order to exploit the spatial uncorrelation of rain events. In this case, the definition of proper handover strategy is of paramount importance for the quality of service management, in order to guarantee the defined performance requirement, avoiding packet losses due to outage event, and on the same time minimizing the satellite bandwidth waste. In this work, we are proposing a handover strategy aimed to properly balance the incoming traffic flow through all the available gateways in order to guarantee the required performance to each traffic flow, exploiting the available knowledge about the network status, such as the gateway's buffer occupancy and the feeder link conditions, measured in terms of SNR values, which are also used to predict possible future outage events. In this slide you can see a schematic representation of our reference scenario, which is a star multi-beam multi-gateway satellite network. The ground segment is composed by a set of n gateways, also called ground stations, whose feeder link towards a geosatellite operate at KV frequency bands. A distributed network of network control centers are also included in our architecture, whose aim is to periodically collect SNR measurement of each feeder link. These measurements are stored and processed by a centralized entity called central node for the outage prediction purposes. The SDN concept has also been integrated in this architecture to properly distribute the incoming flow to all the available gateways and to upload this traffic flow gateway association considering the output of the prediction algorithm and the current status of the network. The considered system model made also the following assumption. We considered C different traffic parameter classes which generate data packets at different bit rate and which require different minimum performance in terms of guaranteed throughput. In this way, the current mean input data rate for each ground station can be computed. Just knowing this information and the number of currently flow associated to each ground station. Information about the current buffer occupancy of each ground station is also known by the central entity and periodically exchanged from the gateway to the central entity. And current mean achievable output rate by each ground station can be assumed known, knowing the SNR measurement and the consequent employed mod code and their spectral efficiency. Our proposed handover strategy is mainly structured in 4 different phases. The first one is called the traffic flow association. When a new traffic flow enters the network, the central node has to decide to which gateway associate this new flow. And to do so, it computes the quantity described in equation 1 for each available gateway, and select the one which maximizes this quantity, which is based not only on the currently known information about the mean input and output rate, but also the estimated value of the achievable output rate by each gateway in a fixed future time windows whose length is p. The second phase is called traffic flow reallocation. When the quality of a feeder link starts decreasing, the difference between the current mean input rate and the mean output rate can become higher than zero, which lead to an increase of the gateway's buffer occupancy and possible consequent packet losses due to buffer overflow. In order to avoid these losses, our proposed strategy reallocates part of the traffic flow from the gateway which is suffering from congestion to another one selected from the available gateway set. In particular, the new selected gateway is chosen using the criteria described in the previous slide. The number of traffic flow selected to be reallocated is the minimum one required to re-establish the normal situation in the congested gateway. And then the SDN switches flow tables are updated accordingly in order to allow the direct forward of the new incoming packet of the reallocated flows to the new selected gateway. In parallel with the previously described two phases, the central node periodically performs outage prediction, and in particular exploit the knowledge about the past and present SNR values to estimate the trend of this variable in a fixed length time windows in the future. If an outage is predicted to a certain gateway, the central nodes compute the amount of data that gateway will still be able to upload to the satellite before the outage begins, as described in equation 2. If this quantity lambda is greater than the current gateway's buffer occupancy, the SDN switches keep forwarding packets to that gateway in order to avoid satellite bandwidth waste. However, this quantity is keep computing over time until its value goes below the current gateway's buffer occupancy. When it happens, the reallocation process starts reallocating all traffic flow from that gateway to another new selected one. However, it is also possible that when the quantity lambda n is computed for the first time, which is when the outage has been predicted, it is already lower than the gateway's current buffer occupancy, which means that the gateway will not be able to upload all the packet already stored in its buffer before the outage begins. To overcome this situation, our proposed strategy will reroute part of this packet storage in the gateway which will suffer from outage to another gateway selected using the same criteria described in the previous slides, following equation 1. After obviously doing an additional control on the new selected gateway's buffer in order to be sure that in that gateway there is enough free space to store these rerouted packets. In order to assess our proposed strategy, we implemented a simulation environment based on the Python's SymPy library. In this table, you can see some of the value of the main parameters related to the simulation environment, such as the number of gateways in the simulated network, the gateway buffer occupancy and the number of traffic class, and some considerations and assumptions we made. For example, we simulated constant bit rate traffic flows. We randomly generated both start time and priority classes for each flow. We generated the attenuation traces following the procedure described in the paper mentioned on bottom of this slide. And we used the linear regression for the SNR estimation and the outage prediction. The results obtained by our proposed strategy has been compared with three other strategies in the literature. Static strategy. Traffic flow are always rerouted from one gateway to another following static decisions which do not depend on the current network status. Network coding based. When an outage is predicted, a block of network coding packet is generated from the block of original packet stored in the gateway, which will suffer from outage. This block of network coding packet will be forwarded through the terrestrial segment to another dynamically selected gateway. The transmission is considered successful if at least a portion of the original plus network coding packet is received by the satellite. Drop strategy. When an outage event begins, the packet stored in the buffer of the ground station which is suffering from outage are dropped instead of being rerouted. Even if the overall simulation duration has been set to 100 days, in this work we included the results obtained with smaller time windows which contains just one outage event which will affect the G0 gateway, as shown in looking at the SNR feeder link traces in this slide. Here you can see the obtained performance in terms of gateway's normalized throughput. When all the gateways have the same SNR values, the central node homogeneously distributes the new incoming traffic flows to all the gateway set, as testified by the gateway normalized throughput values. When G0's channel quality starts decreasing, we can see fluctuation on G0's and T due to the formed unbalanced situation among gateways, which is automatically recovered by the traffic association process. However, when G0 approaches the outage, its channel quality rapidly decreases, leading to congestion due to the severe imbalance between overall input and output rates. Our solution is the only one among those considered which can sense this situation and trigger the traffic flow reallocation procedure, avoiding packet losses and keeping guarantee each traffic flow's required throughput. Looking at G0's and T right before the outage beginning, it never reaches the maximum value with our solution, unlike with the other ones, avoiding an increase of the gateway buffer occupancy and consequently possible losses due to buffer overflow. In this slide, the normalized throughput of the traffic flow affected by congestion is shown, which is the ratio between the actual amount of data sent to the satellite and the amount of data that would have been sent to that satellite in the same time interval to satisfy the defined QoS in terms of traffic flow throughput. Looking on top left, the employment of our solution guarantees the required throughput of the analyzed traffic flow for all its duration, while it cannot be fulfilled by any of the other considered strategies. The performance advantages obtained by using our proposed strategy are also highlighted, looking at the obtained normalized throughput of a traffic flow associated to a gateway when it starts suffering from outage. Also in this case, employing our proposed strategy, the central node starts reallocating the traffic flow from when it sensed the congestion before the time instant when the outage begins. And so possible packets stored in G0 buffer when the outage starts are homogeneously distributed to all the other gateways, avoiding both the network throughput spikes obtained in both static and network solutions, and the packet losses obtained using the dropped solution. An additional set of results has been obtained simulating variable bitrate traffic flows, whose behavior is more similar to real traffic flow than the CBR ones. In detail, we simulated the burst traffic flows with on-off periods of equal duration, duty cycle 50%, where no packets are generated in the off periods and packets are generated in the on periods at twice the data rate reported in the table of the previous slides. The normalized throughput trend, as you can see in this figure, reflects the fluctuating trend of the number of generated packets over time and shows the wider range of values of G0's normalized throughput, which in some time instance reaches the maximum value. However, the additional information regarding the obtained results and the control overhead of our proposed strategy confirms its correct behavior and its robustness even in case of VBR traffic flows. To conclude, this paper proposes a handover strategy for satellite terrestrial communication networks exploiting the smart gateway diversity concept. Our proposed solution exploits the available information about the current network status, in particular the past and measured feeder links SNR and the current gateway buffer occupancies, to move traffic flows and data packets among gateways in case of congestion or outage events. A prediction algorithm is also employed to predict outage events and allow the network to properly react in advance in order to minimize additional delays and satellite bandwidth waste. A performance evaluation phase has been performed through a simulation tool comparing our proposed strategies with others in the literature. Thank you for your attention.